These two forces are equal in size and opposite in direction. If you add them as vectors, the resultant force is 0, and yet the handwheel still turns. Why? Vector addition gives the overall force, but not where each force acts. For an object with size, that matters. The moment of a force about a point is the force multiplied by the perpendicular distance from that point to the force's line of action. In symbols, moment equals Fd. The word perpendicular is the important part here. Place a 400 Newton case at the 3 meter mark on a horizontal ramp and its weight acts vertically, so the perpendicular distance from the hinge is 3 meters. The moment is 400 multiplied by 3, 1200 Newton meters clockwise. Now raise the ramp to 60 degrees. The case is still 3 meters along the ramp, but there is no longer the perpendicular distance to the vertical weight. The horizontal lever arm is 3 multiplied by cosine 60, which is 1.5 meters. The moment, therefore, falls to 600 Newton meters. When the ramp is vertical, the weight's line of action passes through the hinge. The distance and therefore the moment about the hinge is 0. The weight itself is not 0. The common mistake is to measure the point where the force acts. Instead, extend its line of action and mark the perpendicular distance. Write the new unit as Newton meters, not joules. A moment is a turning effect, energy is a different physical quantity. Return to the handwheel. These forces form a couple, equal and opposite coplanar forces acting along separate parallel lines. Their resultant force is 0, but both forces turn the wheel clockwise. The moment of a couple is one force multiplied by the perpendicular distance between the two lines of action. Each force is 50 newtons, and the separation is 0.40 meters. So the moment of the couple is 50 multiplied by 0.40, 20 Newton meters, clockwise direction. Do not multiply this answer by 2. About the center, each force has 0.2 meter lever arm and produces 10 Newton meters. 10 plus 10 is 20, so the full separation already includes both contributions. The moment of a couple is also independent of the point about which the moments are taken. Vector addition answers the force question. The resultant force is 0, so for an extended object we must also check the resultant moment, which here is 20 Newton meters. Now hold the 4 meter ramp horizontal with a vertical cable at its far end. The case weighs 400 newtons at 3 meters and the uniform ramp weighs 200 newtons. The ramp's weight acts through the center of mass. Because the ramp is uniform and regular, this is its geometric center, 2 meters from the hinge. Static equilibrium requires 0 resultant force and 0 resultant moment. The principles of moments express the second condition. Total clockwise moment equals total anti-clockwise moment. Take moments about the hinge. The hinge reaction acts through this pivot, so its perpendicular distance and the moment about the hinge is 0. The force itself need not be 0. The case produces 1200 Newton meters clockwise, and the ramp produces 400. Together, that's 1600. The cable produces T multiplied by 4 anti-clockwise. Therefore, 4T equals 1600, giving a cable tension of 400 newtons. Now balance the forces separately. The weights total 600 newtons downwards, the cable provides 400 upwards, so the hinge provides the remaining 200 upwards. Both equilibrium conditions now hold. In an exam, draw and label every single force. Extend the lines of action and mark the perpendicular distances. Choose a useful pivot. Balance the moments and then check the forces separately. A pivot on an unknown force's line of action often removes that force from the moment equation. That's the full test for this ramp, 0 resultant force and 0 resultant moment. Next lesson we'll be looking at moment graphs and the SUVAT equations.